Welcome again to Industrial Engineering 537, large-scale systems. We're going to get into some what I find intriguing topics today. We're going to talk about a sixth modeling paradigm, and I'm also going to introduce how you tie all of these myriad modeling paradigms together at the end to get a much more effective analysis tool. All right. So topically, those are the two principal topics today. And the sixth modeling paradigm I mentioned is discrete event simulation modeling. Focusing on that now, what is discrete event simulation? Well, it's a collection of models that focuses on operations of a system, sort of the process orientation. And it has to do with modeling discrete sequences of events in time. There are different approaches to doing that. One approach is to pick a fixed time slice in the simulation, and at each one of those increments, they could be seconds, minutes, hours, days, whatever it might be, the simulation stops and calculates whatever has transpired in the preceding interval. The other way to do it is what we call next event simulation. And with next event, you simply schedule events on an event calendar, and when that event comes up, that's when the simulation essentially stops and does all the appropriate manipulations to bring everything up in time again. But in each case, each event occurs at a particular instant in time and marks a change of the state of the system. And between those consecutive events, no changes in the system is assumed to occur. So the system can essentially jump in time from one discrete event to the next. That's quite different than what we've seen with the other two simulation techniques that we've talked about, namely the NetLogo for doing agent-based modeling and the systems dynamics with VinSim. So that's the distinct difference, and its process orientation really marks the topological difference between the two. The other thing to think about is this notion of what we mean by discrete in contrast to continuous. When Jay Forrester first came up with the continuous simulation philosophy back in the 50s, a long time ago, he came out of a world of continuous modeling in the sense of differential equations, partial differential equations, and so on. And so with the notion of system dynamics, he essentially brought that mentality, the mentality of continuous simulation. Now, with discrete event simulation, in contrast to continuous, obviously we've drawn that contrast even sharper. And it's not unlike what you hear about in the IT world when you hear about things like going from analog to digital. Albeit with system dynamics, obviously it made that transition many years ago to the digital world. Nevertheless, it still has that continuous flavor to it. So the contrast with continuous simulations, in which the simulation changes continuously over time, this one with discrete event simulation is more event-based. And so it's called sometimes activity-based simulation. Time is broken up into very small time slices as a rule. And small is, in the eyes of the beholder, it could be eons, depending on what you're simulating, or it could be nanoseconds. And the system state is then updated according to a set of activities happening at that time. So because discrete event simulations do not have to simulate every time slice, they can typically run much, much faster than corresponding continuous simulations. That's an advantage. It all obviously has disadvantages, and I'll touch on those a bit when I get into the stochasticity nature. And that's what this is about, the contrast between deterministic and probabilistic systems. And again, I'll do the contrast with system dynamics, and you've been exposed now to VinSim, which is sort of an industry standard. just as NetLogo is sort of the industry standard, if you will, for agent-based modeling. With discrete event simulation, one of the principal reasons it was introduced was to account for uncertainty. And if you reflect back on what stochastic processes are, it's a random variable index typically on time, albeit it doesn't have to be time. And that's where the randomness comes in. You have a random variable. It has an underlying probabilistic structure to it. Discrete event simulation was built with that intent to be able to simulate, if you will, and model and collect results to understand the impacts of these uncertain or stochastic elements in it. And when you get into these complex systems, get away from the very simple ones, but more into the complex ones that we have been dealing with and continue in this class, it is essentially analytically intractable to find a closed-form mathematical solution to the underlying equations that have random variables. You just can't get there with just mathematics alone. Hence, this notion of Monte Carlo techniques was introduced into this world of discrete event simulation. With Monte Carlo, the reason we've gone to that terminology is we're essentially throwing the dice inside the computer. So we'll come up to a point, for example, where we want to branch between two different, say, nodes in a network in a discrete event sense, and we're trying to decide which way to go. And we'll say from historical evidence, we know that it's to branch left, we'll say, is much more likely than to branch right. And putting a number to that, let's say to branch left, there's a 90% chance, while branching right then is a 10% chance. So the way we handle that in a Monte Carlo world with discrete event simulation, we have a random number generator inside the software that essentially throws the dice for us. We make a draw, and if that number in that case is less than, we'll say, 0.9 on a 0 to 1 scale, then we'll branch left. If it's greater than 0.9, we'll branch right. That gives rise to that 0.9, 0.1 split at that branching node. Another way it's used throughout, fundamentally, is suppose we have decided, yeah, we're going to branch left. We drew that 0.9 probability, but we don't know how much time it takes necessarily to travel along that left branch to the next node. We do know that there's a probabilistic distribution describing that time to go from where we just branched from to where we're going to. And let's say hypothetically that time we've decided is has a Gaussian distribution, just a normal bell-shaped curve, if you will. And let's say hypothetically it has a mean of 100 seconds and a standard deviation of 10 seconds. Well, we have within the library of probability density functions in the code, we have the Gaussian distribution expressed mathematically. So we just simply make a draw from that density function, and let's suppose that it comes up 98, with certainly within the realm of possibility, with a mean of 100, standard deviation of 10. So we schedule the next event in the discrete event simulation 98 units from now, because that's what the draw told us. So there in that one branch, we've used this notion of a Monte Carlo technique twice. Once to determine which branch to take, and a second time to determine how much time it takes to get from where we're branching from to where we're branching to. And that's fundamentally what we use throughout in Monte Carlo. There are other variations of that, and there's a whole host of theoretical distributions, for example, we could use to determine the time to traverse these branches. It doesn't have to be Gauss. It could be triangular, it could be uniform, it could be just virtually anything, literally, because we can also use an empirical distribution function that we have created. So it's Anything we want, in fact, can be incorporated. That process is used until the end of the simulation run. So you can imagine at key points along this network that you're simulating, you're going to collect data. How long does it take for us to get to this point? How many people or transactions got to that point? So we have a statistical collection function embedded within the code as well. So what we call replication through that, we would collect that data. And then we erase everything and start again. And run another replication through a network and collect that data. And we might replicate 1,000 times. And each one of those replications, we collect data. So we're building a statistical picture, if you will, a probabilistic picture of the behavior of a system over time. And once again, that reflects back to the Monte Carlo nature. We're essentially throwing dice on every one of these replications, and we're collecting data throughout the simulation to determine the behavior characteristics of that system. Now, that's fundamentally different than the approach that's implemented with either agent-based modeling or system dynamics. Nevertheless, there are ways to include uncertainty in stochastics. It's not unlike what we've talked about here. They're based on Monte Carlo as well, just that Monte Carlo was introduced initially with this discrete event simulation paradigm. The gentleman generally recognized as the originator of discrete event simulation programming languages was actually a level 1 manager at IBM. And they led in the development of the general purpose simulation simulator, GPSS. That was the original brainchild. And this was back in the 60s. And that has evolved over time, and I've listed a number of current discrete event programming languages. And you see, you may have heard of some of these: SimScript, Simulus, SLAM is simulation language for alternative modeling, Arena, AutoMod, and Simio. These are sort of state-of-the-art today, but again, they are focused primarily on discrete event simulation, which is good. I mean, if you want the state-of-the-art, you go to things like Arena or Simio for discrete event. If you want for state-of-the-art in system dynamics, you go to something like Vensim. If you want state-of-the-art, industry standard, maybe it's a better word, in agent-based modeling, you go to the academic, primarily the world, and that's NetLogo. Anyway, there's a very good account of discrete event simulation and the history of it, and you can access it at this URL that I've shown. And I'm also going to include that paper as a PDF in our class webpage. So either way, and I encourage you to take a look at it if you're at all interested in the history of these things, which sometimes can be quite enlightening. There's another modeling language out there now that I want to introduce you to. AnyLogic is the name of it. And although it's not as well known as, for example, Vensim for the system dynamics world, nor NetLogo for the agent-based modeling, nor Simio, we'll say, for discrete event simulation. As it happens, AnyLogic accommodates all three of those modeling tools, those paradigms. So I want to focus on that a bit because it does lead us naturally into the second topic for the day, that of federation. All right, at this point, what I want to do is encourage you to go to that website and download a version of AnyLogic, and it's a PLE version. And the PLE version stands for Personal Learning Edition. It's free, essentially. Now, you can't do all the wonderful things you can do with the more advanced versions that cost money, but you can do enough for our class. So go to that site and download the PLE version, bring it up, you might want to pause the lecture at this point and then come back where you left off. I'm going to now bring up a specific, the PLE version I've downloaded, and we're going to just dabble a bit with creating a model. It's going to be a very simple model, the bank teller example. Okay. So this is the bank teller example that I created. What I want to do is just show you how to get to this point. So we're going to open up a new model. And we'll just call it BANK SIM, Bank SIM. And in Bank SIM, first thing we want to do is create the arrival of customers to the bank. So we have to have a source. And when they arrive, they're going to have to get in line to wait for, we'll have them arriving at an ATM machine. And when they arrive to the ATM machine, there may be somebody in front of them, so they'll have to wait in line, a queue. And there'll be a delay then associated with that, and we'll call that delay ATM. How's that? And then once they've finished, we'll just send them out, and that's called a sync node. So quite simply, now we have created a very simple model of an ATM at a bank. We get inside each one of these, for example, the source. I'm going to make this window a little larger over here. And so we're going to say we have 1 per second. We have a queue. We might want to reset the queue size to maybe 15 people. 100's a little large, I would think. And the ATM. Here we can, in this case, we have specified that, you remember I mentioned that you can put different probability density functions in to represent how much time transpired, in this case, to get through the ATM. And what they have shown here in the example is a triangular density function. And with the triangular, all you need are 3 parameters, and it's completely specified. So the first one is, what is the minimum value? And again, you imagine a triangular representation of the density function on a graph. So the minimum value they show is 30 seconds. That seems about right for an ATM. If you arrive, it'll take you at least 30 seconds. A minute is they show as the average or mode, the mode, most likely, and the maximum 90 seconds. I'm going to put the maximum a little bigger. I think the maximum might be 3 minutes. And I think the mode, most likely, might be 90 seconds, we'll say. All right. So I'm just trying to give you a sense for how you can manipulate these parameters and change the values of the things like capacity. And then if you look at the top of the bar where the cursor is right now, the little pointer pointing at a little arrow, the green background, if I click on that, it brings up another screen and allows you to, it's basically what we call compiled that model description. And I click on run, you can see it's actually running. If you look closely, the numbers are just to the right and the left of each one of these little icons. So there have been 7 customers, 8 now, 9 go through the queue, 7 through the ATM, and 8 now have left. If I want to bring that up a little bit, if I simply point at the Q, for example, and click on it, it brings up a little larger screen that shows those parameters and labels them for you. You can enlarge it. So I've had 22 come into the queue, 18 leave it, and on average I had 3 people waiting. It's a pretty popular ATM. Anyway, it shows you in real time what's happening with the queue. Move that box over out of the way a little bit. Let me bring up the ATM. And you can begin to see the same sort of thing here. It shows you what's happened. So anyway, you get the idea. It's fairly straightforward to use. I'll call it user-friendly. They become a lot more complicated than the simple one I've shown you here. And I encourage you to explore some of those. And you quickly get an idea of what I'm talking about. Let's see here. Just bring up one more here and see what I can show you. All right, now this one is one I played with before. What I've done is add a little more to it. There may not be, this is just an exclusive ATM machine. It may be that there are other services inside the bank, like with the teller. So what I've shown here in this very simple expansion of it are some tellers, 4 tellers. Customers come in. They could go to the ATM, or they could probabilistically branch, in this case, and go to the teller. And I mentioned that probabilistic branching a few minutes ago. So essentially when a customer arrives, the dice are thrown, and you tell it in advance what the probability of a teller or a ATM demand is. In this case, I chose the number 0.5. So a 50-50 chance when a customer arrives, they'll go to the teller versus to the ATM. So that's what happens here. When the transaction or customer comes in, gets to this node, a random draw is made with the dice, and they'll either be sent to the ATM or to the teller. If they're sent to the ATM, you've seen how that process works. If they're sent to the teller, there are 4 possibilities, and they could be required to wait in the space out here if all 4 tellers are being occupied. These are the customers waiting and being serviced by these tellers. So once again, if you just elect to click on it, run it, it's now simulating the arrival. I can speed it up by clicking on this little circle dial up here. Now I've got it running 10 times what the real world data told it to do. And so you can see the numbers accumulating much more quickly here. If I bring this one up, looking at what's happening in the tellers. So that gives you just a bit of an exposure to what we mean by discrete event simulation modeling. Going back to where we were in the presentation. All right. So I've highlighted the fact that we have these 3 different dynamic simulation modeling paradigms focused on dynamic simulation here. We also have the other 3 paradigms we've introduced in this module. We have the risk analysis, we have decision theory, and we have game theory. One can argue that there are elements of dynamics in those, but I've chosen to label these 3 in particular the dynamic system modeling paradigms as opposed to the others. And once again, the industry standard, if you will, for agent-based modeling is NetLogo. That for VinSim is system dynamics, and discrete event simulation. I've chosen to show you any logic here, but I'm not going to claim any logic is the industry standard. It's probably more something like Semio. Nevertheless, I had a reason for exposing you to any logic here. Namely, I want to talk about federation of paradigms. Let me emphasize that in our class, the problems we've explored can be very wicked. Hopefully you know what wicked means now. And they are typically associated with systems that have one or more of the following characteristics: complex, intelligent, adaptive system of systems, and they have emergent behavior. You have now seen and had experience, hopefully, with risk analysis, decision theory, game theory, system dynamics, and agent-based modeling, and now discrete event simulation with any logic. The point I want to make here is it's not unusual. In fact, it's likely that more than one of these modeling paradigms, these 6 modeling paradigms, will be of value in exploring the solution space of this class of problems, these complex adaptive system of systems problems. Well, if it's true that more than one is going to be of value to you, then it should be obvious to you that you need to start asking the questions, so how do I use more than one of these at the same time? That's where federation comes in. What I want you to do is a little thought experiment. I want you to imagine a metasystem of these modeling paradigms. And this metasystem consists of a collection of all 6 of ours. One could argue that there are other modeling paradigms that could be included. I think 6 is enough for our purposes in this class. So let's just stay with the 6. You recall the Aristotelian notion that he introduced a couple of thousand years ago, that a system is more than the sum of its parts. So you need to think that way when you think about these modeling paradigms. These 6 different tools can be used synergistically to capture and even make use of or exploit this moreness that Aristotle referred to. And a couple of other terms that are useful to you. We're not going to, certainly not going to get into how we'll be implementing high-level architectures in our runtime infrastructures. But we're going to, it's important for you to understand what these notions mean, because you may very well be in a position to use them in your next, as you're doing analysis of these complex systems, say at your workplace environment. So first of all, the high-level architecture. That's a general purpose architecture for what we call distributed computer simulation systems. And using HLA, these computer simulations can interact. They can communicate data and synchronize actions with other simulations, regardless of the computing platform. So what that means is, for example, you could have a system dynamics model and an agent-based model and a discrete event simulation model of some phenomenology, all addressing the same complex system. And a high-level architecture would allow them to communicate with each other. Now, the interaction between those simulations is then managed by what's called a runtime infrastructure, an RTI. So both those terms are relevant and important for you to understand, at least philosophically. Okay. Now, to get this federation, you can think of it as building, at least conceptually, building this matrix. In the matrix, what I've shown is a 6x6 matrix where I have the modeling paradigms listed along the rows and along the columns. So risk analysis, RA, is denoted as RA in the column heading, and so on. For each cell in this matrix, what we're talking about is, for example, risk analysis. And let's go to the first row, third column, with game theory, GT. So this first row, third column, what we are thinking about in the cell of that matrix is what is flowing from the federate, we call these things federates, what is flowing from the federate to the other federate, so from risk analysis to game theory. Terminology-wise, that's what we meant by these, showing these back here. The two important terms that are in the high-level architecture are the federate, that's an HLA-compliant simulation, and a federation, so that's the collection of these things, multiple simulation entities that are running concurrently. And as I've shown on that matrix, the federates we have are these 6 modeling paradigms, and the federation is the collection. Could be 2, but it has to be at least 2 or more. So that's what's shown notionally here. So the idea would be to structure this 6x6 matrix and explore each of the 36 cells in this matrix and ask yourself the question, is there something important in the way of information that should be flowing from this federate on the row header to this federate on the column? And that, you'll notice it also includes diagonals. So it is conceivable you could have multiple, say, game theoretic models running where you'll have, say, 2 games. And the result of one of the games would feed and inform the result or the input to the other game. So every cell in this 36-cell matrix should indeed be explored when you are looking for federates and federations. Types of federations that we think about here, what I've listed, are both qualitative and quantitative. And let me give you a sense for what I mean by that. First of all, in the qualitative world, I want to give you an example that's taken from our Neo-Luddite problem that you've now been exposed to throughout the semester. And with that one, let me close this. What I've done is taken an example where we use 5 of the federates, risk analysis, decision theory, game theory, system dynamics, and agent-based modeling. I'm not going to dwell on these, but it'll be in your on the class page if you want to bring this up. So, for example, what's feeding game theory from risk analysis are consequences, likelihoods, mitigations of conducting peaceful operations, determine disarm that's cooperative versus arm non-cooperative outcomes. So that's what would come from risk analysis and feed game theory. You'll also notice that we have risk analysis feeding risk analysis on the diagonal. Consequences, likelihood, mitigations, and so on determine the level of risk. I'm not going to go through all 25 of these cells, but it's there for your perusal. I strongly encourage you to take a careful look at it to get a sense for what we mean by qualitative federation of these paradigms. Let me go back now to slides. Catching up to where I was. Okay, so we've talked about qualitative a bit, and I do encourage you to go to that matrix on our class page and take a very careful look at it. And you might even want to fill in some of the blanks that are not filled in on that 25 cell matrix. I think that would be instructive for you. If you have questions about that, I encourage you to either email me or call me during my class hours and we can discuss it. Okay. Now, imagine taking that same 5x5 matrix and now going in literally and putting some numbers in it. So you might run, for example, an agent-based model and get some data about the survivability of some of the combatants. And you might want to import that into, say, a system dynamics model. Well, you can literally manually do that, run the agent-based model, write down or record somehow in the computer, maybe in a spreadsheet, some output results. Now call up your system dynamics model and manually input that data. You have effectively achieved a federation at that point, manual. Now, most of us would like to think we can make a transition beyond the manual and get into a runtime infrastructure. I'm not going to be asking you to do that literally in this class, but I am going to tell you you have the capability with the AnyLogic platform. With the AnyLogic platform, you do have those three fundamental modeling paradigms, the agent-based, the system dynamics, and discrete event. And it turns out, the reason I'm introducing you to the AnyLogic, it supports that federation, has a runtime infrastructure supported that's Java enabled. So if you know Java and you become familiar with AnyLogic, you're going to be in a position to run essentially a federated modeling tool on your problems, and that's extremely valuable. This is the way it conceptually does it. AnyLogic has the ability to run any of the three separately. You can build a discrete event simulation model, or an agent-based model, and or a system dynamics model. And you can actually couple those through a federation. Think of these blue arrows connecting them as Java code. That's essentially the language of choice that they've used in AnyLogic. So it's there for you. And what I'd like to do is just give you a sense for how that plays out in the real world, and the real world being our example. There's an example called the insurgency dynamics model, and it looks very similar to what you've seen with the net logo that we did for agent-based modeling, and it's introduced a system dynamics overlay on it. But in this case, the population that we have that we're modeling are the government supporters, the dissidents, the insurgents, and the removed insurgents. So our insurgents in this case were our weavers, the neo-Luddites that are essentially manufacturing the IEDs along I-25 and deploying them. So this particular model has been developed and refined. It's available through AnyLogic, and I'm going to see if I can draw that up at this point. So we'll go back to AnyLogic. And we're going to now open the insurgency dynamics model. This one takes a little longer to load, but now you can see it. And as I said, it does have both agent-based and system dynamics. So let's go into a full-blown running of this thing. This is a description of what the model does. These are some parameters that you can adjust. I'm not going to play with any of it at this point, but I do encourage you to draw it up and play it. Okay, so this is what it looks like. You can see the agent-based model at the top of the diagram. You can see the system dynamics down here. You can see the interconnections. That's the federation. They're actually talking, communicating with one another. You can see how the population levels are playing out over time, shown in this graphic up here. If you look closely, you can see those lines actually changing. So we have government supporters in the green. It's falling off. We have dissidents on the rise, insurgents somewhat rising, removed insurgents rising. Now dissidents are about to pass government supporters, not a good sign for the government. And you can see the massive flow of agents down here in the agent-based model. You can see the parameters changing down here in the system dynamics model. So it's all there. And this is, as I said, very close to what we've done in our class with our neo-Luddite example. I do encourage you to bring this up, play with it. You might think about interfacing it manually or at least conceptually, qualitatively, with risk analysis, with decision theoretic approaches, with game theoretic, and then even bringing in discrete event simulation thing we just talked about today. So it's a very powerful tool, and one that will do you well later to put in your bag of tools that you can bring to bear on these problems. Well, good luck to you in your pursuit of all these modeling paradigms, and I think you'll find them useful. We're going to include those in the class project, so I encourage you to call me anytime during my office hours, or send me emails if you have questions or comments about these things. So I'll just say at this point, have fun with these simulations. Okay, Michael, that's all.